At the beginning of the 20th century, our understanding of the universe was undergoing profound change. Albert Einstein was formulating general relativity, reshaping ideas about space, time, and gravity. At the same time, intense debates were unfolding about the nature of matter and energy. Physicists like Niels Bohr, Erwin Schrödinger, and others were laying the foundations of quantum mechanics. Yet in astronomy, one assumption still shaped everything. The Milky Way was thought to be the entire universe for astronomers in the early 20th century. This was the universe, a vast, flattened system of stars, the Milky Way, containing everything that could be seen. The challenge was not charting the sky, it was knowing how far away anything really was. That problem began to give way through the work of Henrietta Leavitt. Working at Harvard College Observatory, Leavitt studied variable stars in the small Magellanic Cloud because those stars were all effectively at the same distance. Differences in brightness meant differences in the stars themselves. Leavitt discovered something remarkable. For a special class of stars, called Cepheid variables, the time it took a star to brighten and fade was directly related to how bright it truly was. This relationship between period and luminosity turned a flickering point of light into a measuring tool. For the first time, astronomers had a reliable way to measure distances far beyond the sun. While astronomers were struggling with the problem of distance, theoretical physics was undergoing its own revolution. In 1915, Einstein completed his theory of general relativity. It replaced gravity as a force with gravity as geometry, space and time themselves, shaped by mass and energy. But Einstein did not believe the universe itself should change. Like most scientists of his time, he assumed the universe was static and eternal. To preserve that picture, he introduced an additional term into his equations, the cosmological constant, to hold the universe in balance. Meanwhile, astronomy was advancing in a different way. In California, the Hooker telescope became the most powerful astronomical instrument of its time. Using that telescope, Hubble began applying Leavitt's distance scale to the spiral nebulae. Hubble, too, believed the universe should be steady and unchanging, but his measurements were about to challenge that assumption. Hubble identified Cepheid variable stars inside the Andromeda Nebula. Once their true brightness was known, their distance could no longer be avoided. Andromeda was not a cloud within the Milky Way. It was an entire galaxy of its own, far beyond the stars of our home system, at least 100 million light years away. The universe had just become much larger, even if both theory and observation still assumed it was standing still. As the scale of the universe became clearer, cosmology divided along a fundamental line. There were two competing pictures. One held that the universe was eternal, unchanging in its overall character, with no beginning and no end. This view became known as the steady-state theory, and it was taken seriously by many leading scientists, including Einstein and Hubble. The alternative was more radical. If the universe is expanding today, then in the past, everything must have been closer together, denser, hotter, more energetic than it is now. This picture, which came to be called the Big Bang Theory, implied that the universe had a physical history. For years, both ideas coexisted. The crucial question was not philosophical, it was observational. Could either picture make a prediction that the other could not? In the late 1940s, that question was taken up directly. Between 1948 and 1950, the physicists Gamow, Alpher, and Herman worked through the consequences of a hot, dense early universe. Their calculations led to a striking conclusion. If the early universe was hot enough to shape the matter we see today, it would also have been filled with radiation. As the universe expanded, that radiation would cool, stretch, and fade, but it would not vanish. Even billions of years later, they predicted the universe should still be filled with a faint, uniform background of radiation, a signal that steady state could not explain and the Big Bang required. By the early 1960s, questions about the universe had moved from theory to measurement. At Bell Laboratories, Penzias and Wilson were working with a large horn antenna designed for satellite communication. Their goal was not cosmology. They were trying to understand background noise that interfered with radio signals. They pointed the antenna toward the Milky Way, then away from it. They measured during the day and again at night. The reasoning was simple. If the noise came from the galaxy, the signal should change with direction. If it came from the instrument, the signal should remain the same, no matter where the antenna was pointed or when the measurements were taken. The signal did not change. The signal-to-noise ratio stayed constant. That strongly suggested the source was inside the horn itself. So they checked everything. They tested the electronics, they cooled the receiver, they cleaned the antenna, removing what they later described as excess noise from pigeons. Nothing changed, which meant the signal was real. And it meant the source was not the instrument at all. It was everywhere. When Penzias and Wilson compared notes with the group at Princeton, everything fell into place. Dicke and Peebles of the Princeton group immediately understood what the signal meant. The noise that would not go away was not interference. It was the relic radiation they had been calculating. The cooled afterglow of a universe that had once been hot and dense. With that realization, the steady-state version of the universe collapsed. There was no way to explain an approximately uniform background radiation in an eternal, unchanging cosmos. The Big Bang Theory, once controversial, now had direct observational support. In 1978, Penzias and Wilson were awarded the Nobel Prize for the discovery. And with that, our picture of the universe changed forever. There is one final thread to this episode, and it is a personal one. At roughly the same time that the cosmic background radiation was being uncovered, I was sitting in a lecture hall listening to a very different problem being solved. The speaker was Fowler. He was addressing a question that had troubled physicists for years. If the universe began as hydrogen, how do you get from that to the heavier elements? It turns out, you cannot simply build them up one proton at a time. There are no stable atoms with mass 5 or mass 8. Those gaps make it impossible to bridge from helium to heavier elements by simple fusion. Fowler and his collaborators showed that stars solve this problem in a remarkable way. Inside stellar cores, 3 helium nuclei can briefly combine, forming carbon. That process, the triple alpha reaction, opened the door to every heavier element. It explained how stars become factories for matter, how the elements of planets, of life, and of ourselves came to exist at all. For this work, Fowler was awarded the Nobel Prize in Physics in 1983. At the time, it felt as though the universe was finally making sense. The origin of the cosmos, the origin of matter, a coherent story emerging. But physics has a way of humbling certainty. Because just as the Big Bang was being placed on firm ground, evidence began to appear that we understood far less than we thought we did. And that is where the story goes next. So, come walk with me.